Okay. So after some time, we are meeting after some time. So we have proved the following. We have proved that if rho is a Gaussian state, it means the position and momentum observables, the self-adjoint operators, they follow normal. So is Gaussian state is a Gaussian state on L2 of Rn or the Fock space. This is also same comma of Cn. If and only if rho hat of alpha equal to exponential minus I imaginary, if and only if there exists, let me write that. There exists Lm in Rn, so that L plus Im is in Cn, or Lm as a vector is R2n, and S is a matrix in M2n, or satisfying 2s minus ij is greater than or equal to 0, whatever it means. Okay. So finally, and rho hat of alpha equal to exponential minus I imaginary part of x plus iy L plus Im. Okay. Minus, so here I put a root 2 because I want 2s minus ij. So usually there will be a half here, but I am not using that half. I mean, he's not using the half, so I am also not using it. So x. If there is half, then the condition is s minus ij is greater than or equal to 0. This is j. Where j equal to this 0 minus I 0. Okay.
X plus iy.
X plus iy.
The inner product is of x plus.
Here it is xy. Sorry, it's not x plus iy. It's a xy. Is the real. So it is this. Okay. So yeah. Actually, we haven't quite proved it. We proved one direction. The remaining direction, I have to prove something about the positive definite kernel. Okay, I forgot. So I will clarify it in the next class. Okay, we still have, but we want to consider some, what are all the possible yes satisfying this condition, 2s minus ij greater than or equal to 0. That is our aim now. Okay, so I will finish the proof. I mean, whatever the gap is there, I will fill it in the next class. So today we will discuss this condition, this uncertainty condition, which we have seen that it is basically the uncertainty condition in 2x2 matrices. Okay, so 2s minus ij greater than or equal to 0. So this condition we want to discuss. Okay, all those matrices. So I denote Kn equal to all those S in M2n, or when all those matrices which are covariant matrices of Gaussian. So there is only restriction is on the covariance matrix. The so-called mean, this Lm is mean vector. L plus Im or Lm is a mean vector. So this alpha is in C. Okay. C. So there is no condition about that. So the condition is only on the covariance matrix. So 2s minus ij is greater than or equal to 0. So we want to investigate these matrices, all those covariance matrices, all those matrices which can occur as covariance of a covariance matrix of a Gaussian state. Okay, so that's what we want to do. So for that, we want to prove the following proposition, which is what is called Williamson normal form. This is like something like spectral theorem. Instead of unitary, we will have symplectic operator and get some diagonal form. Okay. But there will be two block diagonals, normal form. For a positive matrix. This is for a positive matrix. Okay. So let S be strictly positive. Okay. you can say, I mean, SXX, that is, the inner product SXX is strictly greater than 0, or the eigenvalues are strictly greater than 0. The 0 is not an eigenvalue, it's invertible. Okay. I mean, we are going to invert it, so that's why we are going to use the inverse. So that is why we are taking as a strictly positive. It's not actually necessary when we later, we can actually see if we have some S, we can add some epsilon to it. Okay, some positive epsilon. So it will become strictly positive. So, and then whatever we want to prove, we can use this theorem. We will add an epsilon, so it will become strictly positive. Then we take epsilon going to 0. Okay. So in this, because we want to take inverse in the proof, so we are assuming S is greater than 0. So let S is strictly positive. Okay. Then this is like symplectic eigenvalues or Williamson eigenvalues you want to call. Then there exists D1 greater than or equal to D2 greater than or equal to D3 up to multiplicity, of course, Dn all greater than 0. With multiplicities all strictly greater than 0. There exists unique. Okay. Unique. Okay. It can repeat. Eigenvalues can repeat, no? That is all called multiplicity. A root can, eigenvalues are root of some characteristic polynomial, and there may be multiple roots. And mention what? Because they are not, they are maybe same. That's what I'm saying. When you write D1 greater than D2, you may not say D1 again and D1 again. No, you may not say. We are saying it. I'm just saying. Okay. There are n of them. So only with multiplicities, there will be n of them. Otherwise, there will be less number of that. Okay. So we write it with multiplicity. Okay. So then there exists a unique set D1 up to Dn and a symplectic isomorphism and L. This is the symplectic. What is the notation? Capital S, I think. Spin 2nr. Okay. This is all those L in M2nr. Actually, if you consider as a complex linear operator on Cn, then it is then it preserves it's invertible and it preserves the imaginary part of the inner product. But here it satisfies this condition. That is L transpose J L equal to J. Okay, it satisfies this condition. This is it, which is equivalent to this, which we have seen. So it is all those matrices which satisfy this. Then there exists a symplectic L such that original operator S equal to L transpose. So this is a 2n cross 2n matrix, and this D are n, there are n number of them. So D 0 0 D. It repeats like this. Okay. It's a diagonalization, but the diagonalization is using a symplectic operator, not just that the so-called eigenvalue, symplectic eigenvalue, whatever you want to call, that repeats. Okay. Okay. So yes, look like this. The point is L is symplectic, but that middle D is not symplectic. Only if you have D inverse, it is symplectic, right? If you have D inverse in the diagonal, if you have any positive operator A and A inverse as block diagonal, then that is symplectic. Okay, the middle one is not symplectic. That will mean that if that is the case, then all operators are symplectic, which is not the case, of course. I mean, we shouldn't get confused. Say? What is D? I'm going to write where, yeah, sorry, where D is equal to D1 up to Dn, right? Okay. This is the diagonal D1 up to D2. Okay. Okay. So every positive operator, strictly positive operator, can be diagonalized in this form using a symplectic linear operator, symplectic isomorphism. Okay. So that is the proof. And this D1 up to Dn are unique. Of course, this D can be changed by permuting, but we are not allowing that. D1 up to Dn. So it is in the decreasing order. Okay. So the D is anyway uniquely determined. So before the proof, I want to write a lemma. Actually, yesterday I canceled the class and postponed it to today because I was having fever, not just that, I was trying to prove this lemma. This lemma is used in KRPs. It's not proved there, but this is proved by some EULA. But I looked at the original paper, I was not able to extract the proof exactly we want. So I couldn't find anywhere in the internet that proof. So I thought I could prove it myself. We were trying to prove that has some issue. Maybe we can discuss it later after this class. Okay, so I still not able to prove. Okay, so once either I will, if I prove, I will show it in the next class, or I will get some other proof somewhere. Okay. I thought, say it again.
He's telling you it as an assignment.
Yeah, we will discuss and then discuss. You try, you can try it as an assignment. But the proof, some proof doesn't work means it will not work. So it will not, certain things doesn't work means we have to see whether it works. Okay. So we cannot try to prove, we should not try to prove something which will not work. Okay. Okay. Now the statement is true, so we should be able to get a proof, some other proof. Okay. I will tell you my idea anyway. I will tell you after this. So if A is a skew symmetric matrix, A in M2n are.
Are you recording?
Huh? Yeah, it's recording, no? Yeah. Hmm.
It is recording.
It is recording. Where is the
blinking dot is it?
Okay. Yeah, it said it's okay. So A is a skew symmetric matrix. This is true for n odd also, but you will get some zeros. Okay, skew symmetry matrix. Then, okay, these following are true. The first two statements are clear. One, the eigenvalues are purely imaginary for a skew symmetric matrix. So you cannot diagonalize it in the real Hilbert space, but you can diagonalize in the complex Hilbert space. Okay, then the eigenvalues are purely imaginary. That is clear since, this is the definition of not A transpose. A transpose equal to minus A. Okay, so lambda bar is an eigenvalue, and lambda bar should be equal to minus lambda. So which means it is purely imaginary. Then two, of course, for any real matrix, complex eigenvalues occur in pairs, of course, because you will get a real equation and lambda is a root, then lambda bar is a root. Or you can directly take the determinant, take the bar, and you will see that lambda satisfies, lambda bar will also satisfy. Okay, so if I lambda nr is an eigenvalue, there is notation for it. Is in sigma of A, then minus A lambda is in sigma of A. This is also clear. And the third one, this is what I want to prove. Okay, there exists real. Of course, by orthogonal, we mean real unitaries are called orthogonal. Okay, so real orthogonal matrix U in M2nr such that UA U transpose is equal to, it will look like this, minus D, 0, D. Sorry, D is here. It's an off diagonal like this, like our J operator, except we have a D there. It is just J multiplied with the diagonal DD. See, if we multiply the diagonal DD with J, you will get this, right? Right, minus I, maybe J on this side. Yeah. J on the right? One of them.
D times identity. Like D00D.
Yeah.
J.
This is just correct. Yeah. Okay. Okay. Yeah. Yeah. Okay. So So the proof later. See, my idea is the following. What I think is the idea is, see, given any real M2 2n cross 2n matrix, okay, I want to, so R2n can be identified with Cn. Okay. Of course, this A can be diagonalized in C2n, but that is not useful because we want to get a unitary in M2n, which is real unitary we want to get. Okay. So we cannot use that U, which is a complex unitary in 2n. We cannot use that. I want to get a real unitary. So what I thought is, I want, if your U is given A is a 2n cross 2n matrix, I want to get a corresponding complex matrix in Cn. Okay. But then it will not be always possible. It should be linear. See, R2n can be identified with Cn. So any matrix will give a function on Cn. Okay, that has to be linear to start with. And I want to do something and get it symmetric. So I thought that either multiplying with I is same as j. So I thought something like this. I take JA plus AJ. A is the matrix, no AJ. Okay. I use this matrix and consider the corresponding matrix in the Cn. Then I found that it actually gives a linear map, the corresponding function. I mean, for linear, you only have to check whether I can be taken out.
Yeah.
Okay, you can take out I from this. J is like I. If you take that, if you take that A tilde is the corresponding thing, this is just I then. There is no J. J tilde is just multiplication by I. Okay, so you will get I here. So it is basically this. And you can see that this will be linear. Okay, in complex linear. And corresponding to A, you will get a tilde, which will be automatically real linear, but you want it to be complex linear. Okay. So how will you define? If you have a tilde, you want to define A tilde x plus Iy. You will define it as A xy. You take A xy and project it on the first n thing. And then Q1 is the another projection. Q1 of A xy, right? This is how you will do. Right? So I could do the calculation and see that this will be linear and it's also symmetric. Okay. So I thought that's very nice. So there will be, then it can be actually diagonalized in Cn using a complex matrix. But you get a complex matrix, n cross n complex matrix. That if you bring it back, it will give a 2n cross 2n real matrix. That actually should work. But finally, the exact mapping, this is not, I'm not getting this, I'm getting for a different matrix. I'm not getting A inside, I'm getting A plus something.
Oh, yeah.
So A plus something, maybe multiplied by J or something. I don't know. A plus JAJ, I think. I get this form for A plus JAJ. A plus JAJ, which is also antisymmetric, right? But from this, I can't get it for A. So maybe the proof will work, or I don't know. I was able to do till then. Then I'm confused for last few days. So I was trying to prove this. Okay. 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 So I have to do so. Okay. So proof later. So now we want to use this. Then it is just easy. Now proof of Williamson form. So what we have to prove, we have a positive operator, yes, strictly positive operator, yes. We have to find a symplectic operator L and the diagonals D. Of course, the D is given by this. So let us first, so given A, S is in, I should have taken A, but it's okay. S is greater than or strictly greater than 0. Okay. Then let A is equal to S power half J S power half. Okay. And this is skew symmetric. Right? This is skew symmetric. Because the first one is symmetric, second one is anti-symmetric, the third one is symmetric. So it's skew symmetric. It's a product of. If you take that joint, you will get S power half minus J S power half. So which is skew symmetric. Okay? This is skew symmetric. So there exists orthogonal or unitaries U in M2N are such that A looks like U which we have to prove U transpose. Okay, by this is U law. This is what is called Euler's decomposition. I mean, the earlier lemma, whatever I have stated, is what is called Euler decomposition. I have the original paper, but I was not having patience to read the whole thing. It's not written in this form. So I am not able to get it. Let me first try to prove it myself, and yeah, let's see where it works. Okay. So A will look like this, right? Okay, now we want to get L. There is a mistake in KRP's paper. It's a typo. See, he says that take L equal to KRP's L. I have to take, see, I took me a lot of time to actually find that that's wrong and the right thing is this. He says L is equal to, he says here. Yeah, L is equal to A power half. This gamma is our U, whatever we have got to U, and D power minus half, 0, 0, D power minus half, which will not work. I tried for a long time unnecessarily and it didn't work. This is not correct. Okay, the right L is this. I spent a lot of time trying to prove which is not true. Okay? So, I mean, it is just direct calculation. It cannot be something else. Okay, things should cancel out and you should get it. So it cannot be complicated. So the right L is, take L is equal to, so he had the D on that side, no? So it should be D power minus half, 0, 0. And interestingly, there is a general version of this Williamson theorem proof for infinite dimensional, okay, by someone whom I know. There also directly the KRP's proof is generalized. There also the same mistake is there. The L is written like that. It is just one hasn't verified the product. Actually, I read this paper five years back. I also didn't find this because we didn't verify it by writing it. We thought it should work. Okay. So then when of course, when I have to teach, I have to write the proof. So then I found that this is not correct. Okay. The right thing should be this. What did you say? There is a J now. There is L equal to, and J D power minus half. D power minus half should be on this side. Okay. And U, yeah, it should be this way. A power half J. This is L. First we have to, so this is the L. First we have to verify this L is symplectic, then it satisfies the condition. Okay, we have to get this, and that will follow easily. Let's see. So first claim L is symplectic, L is in SP2NR. That is, we have to verify L transpose JL should be equal to J. So let us just write it. L transpose will be J A power half U transpose L or L transpose L. This is okay. U transpose okay. Okay, that's okay. U transpose U will be equal to that. Okay, so that's okay. So J A power half U transpose. So I'm just writing L transpose. J A power half U transpose. Then this and D power minus half will come this side. No? I better have it L. Okay, maybe I will verify for L. Oh, so he just missed a J then. No. Okay, this will also work. It's okay. So U transpose, right? U transpose, then D power minus half, 0, 0, D power minus half, right? Then there is a J inside.
Sir, the decomposition is it right?
Which decomposition? The A.
Yeah. How are you taking it?
How was you taking?
8 by half.
Sorry, this is not about that. His A is S power half. Sorry, here it should be S power half. His A is different. His A, I mean, I just copied from there, no, something like that. That's why. So, I mean, I want to get the correct one from whatever he has written. So this would be S power half. Okay. So this would be S. Sorry. This is S power half. Okay, S power half. Have I written anywhere else? Okay. Okay. Yeah. So our A is S power half, J S power half. Okay. Okay. So I have written L dagger, L transpose, right? Then there's a J in the middle. Then I have to write L is this again. So D power minus half, 0, 0, D power minus half. Okay. Then U, right? S power half J. Okay. So now you have J, which is just 0 minus I 0. Okay. If you multiply all those things, you will get, what will you get? J S power half U transpose. I think you will get this. It's a minus here. 0 minus D. Will you get this? You will get this, right? If you multiply the middle one, okay, you should get it. Okay, so okay, so and you'll get a minus out. Okay, the minus D will come down and D will come down. So you get a minus out. Okay, so then this becomes J, and now U transpose. This is equal to nothing but S power half, and so U transpose that is equal to D inverse, right? Sorry, this should be D inverse inside, right? You have D power minus half, D power minus half. If you multiply by J in the middle, you will get D inverse, right? It's D inverse. D is diagonal, so it's okay. So you will get D inverse. Okay. Now, if you have if a unitary operator UA, U transpose, A, U transpose. If you take the inverse, that is going to be U transpose, A inverse. Inverse will come in the middle, right? For a unitary. So this is going to be U. So this is precisely going to be that whatever that A inverse. Right? A inverse. So which is going to be J S power half, S power minus half, J S power minus half, S power half J. So there are so many J, S power minus half will go. There are 3 J's. So we will get a minus 1 from two of the J's, and there is a minus J, which is equal to J. Okay. So this is equal to J. This is simple. Okay. So this works. And this is the right operator which works here also. Okay. So what is our A? What is our L? L is this. So now we compute this. Now L D 0 0 D L transpose. That is what we want to compute. We want to prove that this is equal to S. You want to prove? No. Right. Or we want to prove that L transpose we got, what have we got? No. We do the computation directly. We do this L transpose or L. Let's see what we want. I want to get the S in the middle, right? S in the middle. Then yeah. So L transpose I compute. Okay. I want to prove that that is diagonal DD. Then that will imply L transpose the diagonal DD, L transpose. Will, I mean, we have to take in. So I mean, in this case, I mean, we can use M instead if you want. Our L is actually should be L transpose. The L in the proposition is L transpose. Okay, that's okay. The L is symplectic. L transpose is also symplectic, so it's okay. So L transpose S, L transpose. So L is defined to be like this. What is L? L is this diagonal. Diagonal d power minus half 0, 0 d power minus half. Okay. Diagonal d u s power half g, u s power half g, then s in the middle, then the transpose of that. Okay. So that is going to be minus j, right? The transpose of s is minus j. S power half. S power half, right? S power half, then u transpose, and then d power minus half 0, 0, d power minus half. Unfortunately, we have to go through all this matrix calculation. Okay. Now let's have the d power half there. Let us just compute this. What is this? This term. Okay. So u s power half j s power half s power half j s power half u transpose, right? So right, this is equal to our a square, right? U a square u transpose, right? Should I use u transpose then? If I take L transpose, what will happen? There is some, whether I should have taken transpose or this. That's what I'm, L is this. L is like this, then d power half is there. Then
Yeah. It would have been
Hmm?
U transpose is right.
yeah, u transpose. So I should have taken then the whole thing will change, no? So should I change the whole thing, or if I just put a u transpose here,
Yeah, that would be- yeah, it's supposed to be transpose.
here it's a transpose, right? Okay.
Yeah, it's like really this calculation.
So everywhere it should be transpose. So will it change here? That's what I'm wondering. Will it
Yes,
change?
it is like this is wrong because you have written like U transpose diagonal U is equal to A inverse.
Oh, so it should be u here, right? No, because it's
Oh no, and go to the other side.
no, it will be okay. Because inverse also it will do the same thing. Here also it will be u only, right? Here it will be u. Right? Yeah. Sorry, here it should be u, not u transpose. Right? Here it should be u.
Yeah, it should be.
So the transpose will come here. See, if u, the inverse of ua u transpose is ua inverse u transpose. So, okay, so please correct it. So finally we will get, so it has to be transpose here. So I will get to put a transpose here. I'm sorry. Maybe I'll write it here. Change u to u transpose. Okay. So then we will get a u transpose here and u here. Okay. Transpose here, u here. So finally we get that this is equal to see, this is equal to, you can write it like this, for example. This u is q symmetric. So we have, I mean, a square will be symmetric. So we need to be a u transpose u a u transpose, right? We can write it like this. This. Now this is equal to 0 minus d 0. Okay. 0 minus d 0. That will become d 0 d, right? Minus of this. Okay, and there is a minus, another minus here. There is a minus here somewhere. You got a minus j, no? Somewhere. Yeah, here. Here there is a minus j.
It will be d square.
D square, correct, sorry. So d square, d square. You get d square. And the final thing here, this will just, that will be, so this is done. That is equal to d power minus half 0, 0, d power minus half d square 0, 0, d square d power minus half 0, 0, d power minus half, which is equal to, of course, it's all diagonal. You can multiply in the diagonal, so which is just d 0, 0. Right. It should be d square. I mean, if you have two symmetric matrix, it will give a symmetric matrix like this. But there will be a minus there, yeah. And that minus will cancel with the other minus already there. Okay, so calculation is correct. Eh?
How did you get from this step?
No, this one I'm calculating this. We are actually calculating LS L transpose. Okay, L I have written like this, but I don't want to write that big block matrix. So I just calculated the middle one, which came out to be d square, d square. Okay, now I multiply by these two diagonals and I get just dd, block diagonal dd. That's all. Okay, so we got it. Okay, so Williamson normal form is proved. Okay, this is d, not 0. Okay, so Williamson normal form is proved. Proved. Okay, so now we want to prove that it is unique. Okay, so to prove uniqueness, suppose, so as we see, this is the symplectic matrix which works, not the one written in the paper, okay, which I tried several times. Of course, if this works, I think that shouldn't work. Okay, there should be a problem there. I don't see any reason why that is true. I couldn't do the calculation. So this what works. You can try, you can look at it anyway. Okay. Now suppose there exists suppose there exists d prime, which consists of diagonals, of course, written in the increasing order, d prime and d, such that S is equal to sum L transpose d00 d L equal to M transpose we have two symplectic matrices L and M and two diagonal matrices, I mean double diagonal matrices D prime and D, such that D prime 0, 0, D prime M. These two are equal. Okay, then lemma. Yeah.
What is
The D is the diagonal, D1 up to Dn. Oh, I didn't write it. Oh, sorry.
no, but
Yeah, the D is the diagonal, which are precisely the eigenvalues ID1 up to IDN. Sorry. Where D is diagonal, sorry. D is equal to diagonal. D1 up to Dn. Where IDN, precisely IDJ and minus IDJ are eigenvalues. Values of that E. Okay. Yeah, sorry.
So you're taking the real.
Yeah, the real part, yeah. Yeah. Sorry. I mean, I thought I said it, but I didn't. So that is why I said all this. You have the you have eigenvalues which are purely imaginary. Okay. Then you take the real part of that, the real part of the, I mean, imaginary part of that. Okay.
Yeah.
Okay. So that gives real. Okay. And they are precise. I mean, they form the off diagonal. Good that you asked for clarification. Okay. So it is precisely that D we are using and getting this. So getting this real orthogonal matrix is a problem. So we are using it crucially, so it is needed very much, right? If you use complex one, it will not, you cannot use the complex one to prove this, right? So you need the Euler form. Okay. So now to prove uniqueness, S looks like this. S looks like using a symplectic L and symplectic M. S looks like this. Okay. Then S also looks like L transpose, M transpose inverse, okay. D 0 0 D, L M inverse, right? M inverse equal to D prime 0 0 D prime, right? Okay. So this is equal to N. Let me call this is equal to N. Okay. Then N transpose D 0 0 D N equal to D prime 0 0 D prime, right? Okay. But then this is not enough. But N transpose JN. N is symplectic, right? L product of two symplectic matrices is symplectic again. You can see, okay, equal to J. So this implies N transpose equal to so N transpose equal to J N inverse J, right? I'm just wondering, there shouldn't be any minus, huh?
Yeah, minus.
Let's see. Oh no, what happened? Okay, N transpose equal to, no, that cannot be minus, wait. N transpose Jn equal to J, right? So then you hit it taking N transpose J inverse.
The J square is minus I. J square is minus I.
J square is minus I. Yeah, but J inverse, you are taking J inverse, which is just
So minus
J inverse. Okay, let's put J inverse. Okay, J inverse. This is okay. Okay, J star. Let's not confuse with J. Let's put J inverse. Okay, whatever it is. So because that's what I want to get. I want to get similarity, not the, oh, let's put J inverse. So that will imply that, okay. Okay. So I just write it. I just insert that. Okay. So this implies N inverse J inverse of D 0 0 D equal to, I take the J inverse on the other side also. N equal to J inverse D prime 0 0 D prime. Right. Okay. This is okay. Okay. Now what is this? This implies N inverse. If you apply J inverse is just I mean it is minus I, it is I minus I, right? So if you, yeah, you will get 0, which one? 0 I multiplied with 0 I multiplied with that you will get the D here, right? You'll get the D here. Minus I will get you the minus D here, right? Okay. N is equal to same thing here. 0 D prime minus D prime 0, right? Okay. Now you know that that matrix, similar matrix have the same eigenvalues, right? Okay. So that is similarity. If you can conjugate by, you can use the add map by invertible map. Okay. So that is similar. So the left-hand side has eigenvalues ID1 up to IDN. Right-hand side will have eigenvalues, but ID1 prime up to IDN prime. They should be same. Okay. So this implies D equal to D prime. Since they have same eigenvalues. Okay. The block diagonal D minus D prime, they should have the same eigenvalue. That is a similar matrix, right? That is similar to that. So they should have the same eigenvalue. So D1 up to Dn should be same. So it's unique. It is just the set D1 up to Dn matters because we have arranged it in the decreasing order. Huh?
Like the eigenvalues of that block matrices will be the same as this side.
Right. It's only eigenvalues which matter because we have arranged it in decreasing order. Okay. So there is only one way of writing it. So D is equal to D prime. That's what you want to say. Right. Okay. So this is done. Okay, good. So what is the next one? Next, we want to see what it means for a covariance matrix. Okay. So Kn is all covariance matrix. So did I write it somewhere? Yeah, Kn is all those matrices which satisfy that condition. That is our Kn. Okay. So this is the new theorem. S is in Kn. Maybe I'll write Kn again. Kn, which is equal to all those S in M to N. Such that S 2S minus Ij is greater than or equal to 0. Okay. If and only if and only if what? There exists a symplectic L, of course, which is an sp2nr, spin R, and D1 up to Dn with all Di greater than or equal to half. Okay, that's the condition. And such that S is equal to L D00 D L transpose. Okay. So all covariance matrix, of course, we already know that if it is positive, it is going to look like this. Okay, that we have already, that's the Williamson normal form. The only extra condition is Di should be the uncertainty 2S minus Ij. That condition will imply that they should be greater than equal to half. Okay, that's the only condition. So proof. And that is just easy. So we want to prove that 2S minus Ij is greater than or equal to half. We already have Williamson imply there exists L and D1 up to Dn. D is equal to that D1 up to Dn, right? Such that S is equal to L D00 D L transpose. Okay. Okay. Now 2S minus Ij is greater than or equal to 0, which is equivalent to saying so we have to assume that S is strictly positive, right? So assume, I mean, as I said, you can add an epsilon and do that. So we will do that later. So assume, for the time being, assume S is greater than 0. S can be 0. Covariance can be 0. That will, I mean, some part of it may be 0. Okay. 0 means it's just not invertible. That's all. I mean, the eigenvalue can be 0. That's all. Okay. It's not 0 matrix. So 2S minus Ij is greater than or equal to 0. Which is, so this is equivalent to saying L transpose 2S minus Ij, L transpose is greater than or equal to 0. You know this. If A is greater than or equal to 0, then B transpose AB is also greater than or equal to 0. For all B, for any B, this is true. You just write the positivity condition, inner product, and you will get the B on the other side. And this is just easy. Okay, this is direct checking. You need star when you work with complex ones. Okay? You have to put star when you work with complex Hilbert spaces. So this is true for all of them. So that is equivalent to, I mean, L is invertible, so that's why I put equivalent. Okay, so you can go from here to there. You can go backward also, backward implication also. So that will imply L transpose 2, L transpose, yes, L transpose. But L transpose J, L transpose is just J. Okay? J greater than or equal to 0. Okay. So this just implies that we have our D 0, 0 D minus I by 2 is greater than or equal to 0. Oh, sorry, not I by 2. This I by 2. 0 I times by 2. Okay. Minus I to I 0. This is greater than or equal to 0. Okay. So what is this? Huh?
Okay.
I'm using the fact that L is symplectic. Okay. So now this is equivalent to saying, what will you get? See, what is this? You get I by 2, which is I mean, this is just I times, that off diagonal term is I by 2 times I by 2 in the diagonal, basically. So you have the di's in the diagonal. You will get a precisely this map. This is equivalent to saying di I by 2 minus I by 2, I by 2, di. Let me write it and then tell you. Greater than or equal to 0 for all I. See, I will not write the explanation. I will tell you the explanation. See, what is that matrix? Whatever the condition we have greater than or equal to 0, what does that become? You have a D1 up to Dn the block diagonal. Clearly the same block in the jth place you have a di. Okay, and here you have j plus n jth place you have I by 2 minus I by 2. Here you have j plus nth place in the bottom. You have I by 2. And in the place j plus n place you have dj. Okay, that is what you have. Okay, it is like it's just permuted. It is basically direct sum of these kind of things. Basically, if you want, you can permute, change the rows and columns and bring it to the direct sum of these things.
Could you say that?
I'm just saying that. So first, it's clear that that matrix, whatever that matrix has, jth place there is a di. Okay, here j plus nth place there is I by 2. Here j plus n jth place there is an I by 2. Here j plus n there is a same di. Okay, so you have this matrix. Okay, by shifting the column, by changing the columns or changing the rows, you can write it as direct sum of these kind of matrices. Okay, changing column corresponds to intertwining by the unitaries, permutation unitaries. You know permutation unitaries, so you can the one and the you can that they are unitaries. You can permute the rows and columns. Okay, so the positivity is not going to change by that. Okay, so you have direct sum of these things, and the direct sum of these things are positive if and only if each term is positive. So this matrix is positive. Okay, now a 2 cross 2 matrix, you know that 2 cross 2 matrix is positive if and only if the determinant is positive. For 2 cross 2, you just write it. I mean, you can if you have any. If you have any, let me just tell you, A B C D is positive. Maybe I can put B here because it's symmetric. Okay, is positive. That is equivalent to saying this xy, A B C D xy comma xy is greater than or equal to 0 for all xy. You just write it, you will get a quadratic equation, 2 degree equation, a square, x square, and y square. That doesn't matter. You consider the determinant or discriminant of the quadratic equation. That should be negative. That will precisely give you that the determinant is greater than or equal to 0. Okay, it will be the negative of the determinant you will get, and it's an exercise. Okay, the 2 cross 2 matrix positivity is equivalent to determinant being greater than 0. So this implies di square is greater than or equal to 1 by 4, right? That's what we want. Okay, so di square is greater than or equal to 1 by 4. That also says that the determinant of S. What is this? Yes, we have this. So you know that for a symplectic matrix, determinant is 1. See, if you notice, we proved some structure theorem for a symplectic matrix. If you can look at it, or we have already proved that the eigenvalues of symplectic, if you look at the proof of an earlier theorem, the eigenvalues, either it is equal to 1, or if something, lambda is an eigenvalue, 1 by lambda is also an eigenvalue. We proved that for a symplectic. That is clear from the JL, exactly. S is equal to, L is equal to J L inverse L J inverse. So because of the J L inverse J, right? J inverse, right? So because of that, lambda is an eigenvalue, 1 by lambda is also an eigenvalue. So the determinant will be always, it will come as pair or it's equal to 1. Okay, so it lambda and 1 by lambda will be there, or it can be equal to 1. Okay, so what it says, so the determinant has to be 1. Okay, so that implies that the determinant of S is just the determinant of the diagonal, which is just the product of dA square. Okay, this determinant S is equal to the product of A equal to 1 to n dA square, which is greater than or equal to 4 power minus n. Did I say that determinant of S, the statement? I should have said that. I forgot to say. The dA is greater than 0, and we know that determinant of S is greater than or equal to 4 power minus n. Okay. Okay. So we have proved this. Okay. So the next statement. When I started at 1 hour has passed, no, more or less. Okay. So I will prove the next 2 statements and then finish. Okay. This is something, a structure theorem, but we have to go through the calculation. This is a lemma. I mean, this week it's enough to prove it for a real number. So, because it's all diagonal matrix. Let D be a diagonal matrix. D greater than I be diagonal. Okay. I forgot. So, so this we have assumed that S is strictly greater than 0. If F is, so one way is, so if F is, if S is not strictly greater than 0, if F is not strictly greater than 0, then S plus epsilon times 1 is greater than 0. Okay. And you will apply that, you will finally get that. So from all the calculation, S plus epsilon 1 should be greater than equal to that 4 minus n or whatever. Or you will add that epsilon everywhere. Take epsilon going to 0, you will get the answer. Okay. There is nothing here. Take epsilon going to 0. Determinant is continuous and all that. So that is proved. So now we want to prove the following lemma. So D greater than I be diagonal. Then there exists diagonal matrix D1, D2, all strictly greater than 0, such that D is equal to half into D1 plus D2 is equal to half into D1 inverse plus D2 inverse. Okay, that's all. We have to write it like this. Okay. Proof. Of course, let D1 equal to D2 times some x, which is always the case, right? It's diagonal. So D1 will be, maybe x is, if D1 equal to D2 is identity, otherwise you will get some numbers, right? They are all diagonal. I mean, it's enough to prove this for real numbers, as I said. It's a diagonal matrix is just a artificial one. So anyway, D1 equal to D2x, okay? Then you want to solve this equation. Solve D is equal to half D1 plus D1x. So D1 into 1 plus x. 1 plus x equal to half D1 inverse into 1 plus x inverse. Doesn't matter, they all commute. We have only diagonal, right? So it doesn't matter which I have to write it the other way. I'm writing it this way. It's okay. Okay. So this implies, let me do the calculation. This implies D square equal to 1 by 4 into D1 will cancel, and it is going to be 1 plus x into 1 plus x inverse. Okay. Let me do the calculation once. So that is equal to, this implies, put the 4D square here. I get a quadratic equation in a diagonal matrix, but that doesn't matter. I mean, it's the same. It's the same as quadratic equation in single way. Okay. 4D square equal to 1 plus x into this. So identity plus, I mean, let me write it 1 itself. 1 plus 1 plus x inverse. Okay. So this is 4D square x plus plus 2x plus x square. Is there any other term? There should be three terms, no? Plus 1. Okay. So I write it as a quadratic equation. X square plus or minus maybe. Minus 2 into 2d square minus 1x. Okay, I have taken care of x square. I have taken care of this. I take care of this. Plus 1 equal to 0. So x should be, let's not take the minus 1 because we may end up in negative. So we write it like this. 2 I want to cancel. So 2b square, 2b minus b will be this. Minus b by 2 I am cancelling. I will take the 2 other from the other side also. Maybe I will put a 2 here. Okay, doesn't matter. 2 plus or minus, so plus b square minus 4ac, which is square root of b square is 4. So there is a 4 which I take it out and I forget this 2. So which is just going to be 4d square plus 1 minus 4d and minus 1, minus 4. Something should cancel, no? Oh, this is d square. So d power 4. So this is d square plus 1 d square minus 4ac. So that 4 I'm taking it out. Okay, so it's okay. So this is minus 1 d square minus 4ac. Here I will get a, say I am taking this 2, that 2 4 will be there. So the 4 will be there. And here also 4ac will be there. 4 will cancel. That's what I have taken it out. Okay. So this is okay. So this is equal to I1 plus 2 into d square minus 1 plus this 1 will cancel and 2 into d into d square minus 1 power half. D is greater than 1. So d square minus 1 is positive. Everything is positive. So x is positive. Now you can find what is d1, d2. I mean, we can find what is we have to find one. We have to find d1. D1 is going to be 1 plus x inverse times d. 2 times 1 plus x inverse d, and d2 is like this. Okay. We don't need exact thing. We just have to find its existence. Positive. Right? You can substitute x there. You know d. In terms of d, we have got it. So d1, 1 plus x inverse times d, and d2, we can get it. d2 is just d1 times x. Okay. So we got d. From this, we get d1 and d2. That's all. Okay. Now we come to the theorem. It is the theorem. S is in Kn, then it looks like this. S is in Kn, if and only if and only if there exists L, M symplectic, okay, such that S is equal to 1 by 4 L transpose L. See, it has a nice form now. Okay. And you know that L transpose L, you can always get it as covariance matrix by explicitly. You take the vacuum vector and apply gamma of L on that. Okay, you will get a Gaussian state. We have seen it earlier. I mean, maybe it's a long time now. So several weeks back, we went through the discussion. Take the vacuum vector, apply gamma L on that. L is a symplectic, so you have a gamma L for that. Apply the second quotation gamma L. You will get a covariant Gaussian state with gamma L. The vacuum vector E of 0 is a it is a Gaussian state with covariance matrix L transpose L. Possibly half or something is there. Okay, half of L transpose L. So you will get something like that using that. L is symplectic. Here we are getting something similar. If L is equal to M, then this is just half of L transpose L. We know how to get that anyway. So here, yes, any S has to look like this. That's what we are saying. Okay. So L transpose S from L and L transpose. This is what we want to prove. Okay. So there is something about extreme point. Do you know what is extreme point of a convex set? Okay, maybe if I have time, I will discuss it. We will discuss tomorrow. I will just prove this and finish today. Okay. If it is an extreme point, this is an extreme. This is a convex set. Set of all covariance matrix that Kn whatever is a convex set. You can see that it's a convex set. We'll verify that also. Okay. A convex, then you can define what is called an extreme point. Extreme point if and only if L is equal to M, which means that S is equal to 1/2 L transpose L for some L. Okay. So we will come to that. Define extreme point and come to that. See, if you take all probabilities measure, whatever the extreme point is, it cannot be written as linear combination. It does. There is no line joining them. See, if you have a circle, this is an extreme point. This is a convex. This is an extreme point. You cannot take a line and it does not lie in a line, right? It's any line containing that is containing in the convex set is that point itself. A point is also a line. If you can't take.
Does the extreme point always-
Say it again.
does the extreme point have to be the boundary?
Maybe not always, but you can have complicated figure.
If the convex set is open, then it can't be on the equation.
Yeah. So if you take all probability measure in the classical probability, the extreme points are the point measure, delta measures. I mean, which takes the value 1 at some point and 0 everywhere else, which is a measure, delta measure or whatever. So similarly, the state for a state,
Pure state.
correct, pure state. Okay, pure state are the extreme points. Okay, so here we want to for this Gaussian state, the extreme points are precisely 1/4 L transpose L, which is a pure state, we know, of course. Okay. So we want to prove this proof. Okay, so if S is so S is in Kn, so S is equal to some L transpose. Okay, I want to get a L, no? I want different notation. L, M, N. I put N. N, Z, D. D0, 0, D. N transpose. Okay, it will look like that with each D equal to with D is equal to D1 up to Dn and Di is greater than or equal to half. Okay, that's the condition. We have already got it. Okay. Now, yes, look like this. Yeah. Now we know that D is greater than equal to half times identity. So 2D is greater than or equal to identity. Okay. I mean, we need that condition here, no? Because we are using D square minus 1 and other things. So we have the square root of D square minus 1. So it should be positive. Okay. So D is greater than 2D is greater than identity. Okay. So there exists D1, D2 such that 2D is equal to D1, D2, D1, D2 both strictly greater than 0. Okay, diagonal. Okay, 2D equal to half of D1 plus D1, D2 equal to half of D1 inverse plus D2 inverse. Okay, right. So which implies S is equal to N. We write it like this: D1 0 0 D1 plus D2 0. Here I write D1 inverse 0 D2 inverse N transpose. We can write it like this. The D we can write it like this. The first D I have decomposed as D1 plus D2. Second D in the bottom of the diagonal I decompose it D1 inverse and D2 inverse. So we can write it like this. Now we know that this is symplectic, right?
So,
Hmm.
but that would be D greater than equal to 1/√2, right?
Huh? Yeah. 1/√2. D is greater than half. Okay. So 2D is like this. So D1/2 I need to. D is equal to 1 by 4, right? 1 by 4. So 1 by 4. Yeah. What are you asking?
So the previous one. Okay.
Yeah. I mean, 2D is greater than 1. So 2D can be written like this. Okay. So I got a 1 by 4 there. D is equal to. So now we know that D1 inverse, that diagonal is symplectic. Right? We have proved that everything will look like up to 2 unitaries, it will look like that. In fact, that we proved the structure theorem. Okay. So this is equal to 1 by 4 L transpose L plus M transpose M, where L is equal to N transpose D1 power half 0 0 D1 power minus half times N transpose if you want. And M is equal to D1 power half D1 power minus half, right? So D2 power half 0 0 D2 power minus half N transpose. Okay. So both will look like this. I'll stop here. It's fine. So that's what we want to prove. Okay. So any S will look like 1 by 4 L transpose L from M transpose M. That's what we want to prove.